People have at least heard about the High robot paper. Did someone post that on Discord already? No, nobody's heard about it. I know some people have heard about it. Okay. Um, I just figured this would be a nice motivation for talking about what we're going to go over in class today. So one of the pieces of this new paper, which is now just kind of like two VLMs put on top of each other, one of them is going to specify goals to the lower level chunk of this and figure out how to control those well. I thought there was a diagram. Um, And this has always been a paradigm in robotics for a while. Basically, there's some high-level controller maybe giving navigation commands, and then some low-level controller that's taking those navigation commands, maybe converting them into like leg motions for a robot dog to move, or could be in a car for like controlling how fast the wheels spin and how much it turns. But there's basically very often been like this kind of like decoupling of these two levels, especially in robotics. Like whenever someone uses a PD controller, something also needs to give the PD controller like a goal or a target to go to. So then a lot of what we're going to talk about today is like one of these levels. We're going to talk a lot about the bottom level here. Like how do you make a good goal conditioned policy such that you can specify any type of goal to it and it should be able to satisfy those well. It's been an area of research for quite a long time, and it's coming back into a lot of things lately. Even I think the on the Discord channel we did already share the stuff from Figure, that Helix design, which is also another hierarchical control where like one is a VLM and then the other one is well, we don't have as many details, but it's some other small learned model that takes goals. But a lot of how well these systems are actually going to work is going to depend a lot on how well that bottom like goal conditioned policy machine learning piece is going to work. If it can't do anything, like if you couldn't somehow control yourself, no matter how smart you are, if you can't move like the embodiment of the robot well to satisfy those goals, the reasoning isn't very helpful. Okay. Does that make sense? We're all really thrilled about talking about goal condition stuff for a while. Okay, awesome. Uh, so then I was here. And we'll start with the first chunk of goal conditioning, which is more of the framework here. Okay. So then I put up the slides. There's a couple of papers. You can look at those later. But goal conditioned learning has been around for a little while. So we're going to go over some of the structures for this. We're going to kind of motivate this really quickly by what is a pain about reinforcement learning and then get into like why goal conditioning can be helpful. So we still always have our like second favorite equation in the universe, which is the probability distribution of paths that an agent can execute. And then, our first one and only favorite equation in the universe, which is our reward maximizing sum that we want to be able to maximize. But a question here for like the group. So what if like this trajectory is really, really long? You can imagine it's, I don't know how long it takes you to get, home from here, but if it takes 40 minutes and that trajectory takes that long, is it like easy to be able to train an RL policy to now execute over all those 40 minutes, not make any mistakes and eventually find a goal? Maybe how many of you also had like an easy time getting to Mila the first time and didn't have to correct at all? Totally worked? No, probably not. Me neither. And also there was, I think, a ton of construction outside of that first time we were here too, and the beginning of the year. But so I hope they're done with that now. Then we can actually have class in this room. But there basically becomes this challenge is like the longer this trajectory is, we've already talked about it before too, like the sample complexity and finding an optimal policy depends on trajectory length. So there's a lot of challenges as trajectories get longer and longer for being able to control agents. So then here, we might start to come up with this concept, okay, maybe learning one policy for like one single reward might not be the best way to structure this whole learning problem. Because here it's like train a policy, it has to maybe figure out how to go like 40 minutes long in some trajectory. There's going to be some really challenging long horizon, just the whole planning problem is going to be challenging in the space up to T. There's even going to be credit assignment issues. So remember, part of that sample complexity we talked about is like sample complexity up to t just to find the optimal trajectory. And then now a whole nother process to learn that optimal trajectory to figure out, what were the most important parts on that trajectory to make it happen again. So that's basically us to think of the question, all right, if this is so painful and our problem is as the trajectory gets longer, sample complexity gets terrible, could we split up this problem into like basically subproblems? Does that even improve our sample complexity in that case? So this is where I like to talk about my favorite use case anyway, because at least I like to cook. Um, is there is often a lot of compositionality inside of the types of planning problems that we perform, like even a lot more than you may think. So here's an example of doing this for cooking soup. So sure, the goal for the entire policy could be cook a soup. This might take anywhere between 20 minutes to 3 days, depending on what type of soup that you're cooking. But there's still going to be a lot of similar things used. So like tasks like gathering vegetables or grabbing the salt or grabbing the pepper. There's going to be a lot of basically moving forward and being able to grab some items. So it's going to be like navigate, grab something, navigate, grab. So a lot of those end up looking like the same, basically like goal cycle over again. And we can get even to more details for like cutting a vegetable. Fine. But now you've got to cut somewhere between 1 and 50 onions or something like that. But now each onion is actually the same task. There's nothing really unique pretty much about every single onion. For the moment, we will assume uniformly shaped sizes of onions, and that we can totally just replicate the exact same policy. And even like the muscle motion for doing a chop, that can now just be like kind of pre-programmed where you don't need to figure out how to learn a whole policy over that really repeated behavior really often down to contracting muscles. So there's at least for the cooking soup example, which I picked very carefully, uh, this one is fairly compositional. Okay. Does that make sense? You're starting to maybe start to realize kind of like how mundane and repetitive all the things are that you actually do in life, and that they're actually all little small policies all put together. Yeah. So this is so an example. So here actually, you know what? This isn't one policy for 40 minutes. This is 7 to 8 different policies, most of them only executing for like a second or two. And a second or two is stuff we know how to train. Like we've already done that in the class a couple of times. Not nearly the credit assignment issues. Um, so that's at least a nice conceptual way for talking about this. Now, how the heck do we do this? Now there's going to be this collection of policies. They all do different things. Gonna have to figure out how to sequence these all together, figure out how to use which policy over some other policy at a specific state, and also some additional challenges in terms of representation. So the challenge here now is there's a bunch of different policies. This at least consumes a lot of memory. And it's not always clear on which one to use. Um, so one of the challenges, like the thing that's kind of wrong now, if there is now a policy for all these different things, is they don't get reused, like even in the parameter space. So if there was there's a cut onion here, but if there was also cut carrot, a lot of the similar motions is going to be used for cutting a carrot, uh, especially if it was like cut carrot and then like cut zucchini or something like that. Those are even like, okay, you'll have to trust me on this one for like how cooking works, but it's mostly like the same type of motion and the same type of thing you want. So do you think we really need an entire other policy for cutting carrots versus cutting zucchini? Yeah, I'm guessing. Too many of you do much cooking? Yeah, a little bit. Oh gosh, maybe we need robots more than I thought. There's only like 20% hands raised on that one. But you tend to reuse like these abilities when you're doing cooking. Maybe you've got some other idea and concept in mind for the reuse there. So this is okay. How can the agent or the learning algorithm figure out how to like reuse the structure, like take advantage of this reusable structure? It's not that There's definitely some compositionality here in the goals that can be pieced together, but it's not the best option to just do. Here's a whole collection of policies for every single unique goal or small change. This is also what we'll get to in a little bit more detail, maybe at the end though. Figuring out how to do this splitting and like across like policies and stuff is really the hard part. And this is where like even in the paper for High Robot, they're trying to propose like a particular way to split how like which one of these things are done by which policy. They more or less kind of chop a line right here. So now the stuff on the bottom is one giant policy, the stuff on the top is another giant policy. Is that a perfect trade-off here? Not really. Maybe for the particular types of tasks they're doing. And we'll have probably another like in-class discussion about the pros and cons and challenges of doing what we'll talk about doing hierarchical control in more detail for the next couple classes. Okay, any questions? Like even just about like goals, hierarchical design so far? All perfectly clear? Okay. Let's see if we can fix that. Um, so basically, let's start with like base case on what we could think about adjusting here. One is, okay, maybe instead of some sequence of policies, now let's try to create one policy. So now this is going to be a policy. So we'll have some shared structure. Let's say this is that policy that's just like the cut stuff policy. So C could be carrot, C could be courgettes, or it could also be cucumber, or it can be zucchini. So it doesn't have to start with the letter C. It's just context is basically what this is. Figure out how to do something. Here's a little bit of information that's like slightly different than the state because it doesn't really change over the trajectory that the agent is going to execute. It's a little bit more like a command, something that helps it give it a bit more information about which one of its policies it might execute right now. Okay. And now you could think of this as basically take this I here that was for each one of the parameters, and now this C is just basically like all those letter I's, just like 0 to however many contexts were useful. And this allows now for some option to do this policy reuse. Then at least it is one policy trained over a bunch of these different contexts, but it's at least can share all the parameters for learning how to do cutting. So there's not a bunch of copies of those parameters. Also, another reason why this is nice is it gives a bit more robustness. So now this policy has seen variations, slightly different things to cut. So it should actually become a little bit better at like handling the variations, even in carrot size or something, because it's also seen different sizes of cucumber, something like that. Okay, just a small detail for when this is done in practice, using something that's just a number, like if this was just, some integer from 0 to n, doesn't always work very well. What people tend to use more in practice is a one hot vector. So it's like now this is a big vector. It's all zeros and there's a one wherever it like corresponds to the original number. We can have a longer discussion about why this works better, but partly take my word for it. Second, it's almost like now there's more features in the input space that describe the actual task and it can do a better job of paying attention to them. I've even seen some really unique versions of trying to do this context where actually they turn it into like a whole image and then there's a big giant patch. So it still represents more of the input space to actually get it to pay attention to this more. So just be a bit cautious if when you start doing some goal conditioning, first hurdle to get over is like whether or not your model pays any attention to the context you're giving it. If it doesn't pay as much attention, conceptually, I'll say make the context bigger as if it's like more of a proportion of the actual input, to the point where I've actually seen people like have like one whole channel basically inside of like the image input is now a context, even though it's representing an integer. It ends up being pretty helpful. I've even designed a version of a network that was like this, where it had kind of 4 different chunks of the input. And then these were all fed into the network in the initial layer, and then this corresponded to 0, 1, 2, and 3. So I literally, like, depending on the goal, it's like, no, I'm going to have the whole input go into this chunk of the network instead in the input space, instead of how it was before. So it's kind of like doing it this way: state, state in chunks. And that was a way for me to like really force that it has to pay attention to that. And now that it's being inputted in a different part of the network, it could pick up on different tasks much better. But I was being pretty forceful with that particular arrangement of the inputs. Let's finish drawing this, action. Okay. So now we've got this new policy, still the same shared parameters. This is better. Um, it's at least saving some parameter space and getting some reuse. But what if the goal that you end up wanting to ask this policy for is actually to do some combination of two tasks? Uh, I'm sure for those that are maybe more familiar for cooking, you probably don't do it too often, but what if you're like trying to cut a vegetable and also stir the pot at the same time? Possible, right? If you're like really good at it and you've practiced a lot. So then is it possible to specify this task with that representation? Maybe, might get lucky. There you go. You never get lucky when it comes to deep learning. You just get confused for a little while. But it's not at the moment. Like this one hot vector is like it's been trained to do this specific task. It's sort of like remember, this is basically an input that controls like the probability distribution. And when that changes, it's like selecting a whole nother probability distribution. There's maybe a chance if you get really lucky, like you could put another one here and a one there and see what happens. It's like maybe it'll try and do that task in the other one. There's really not much of a guarantee that that'll work well. Well, like, okay, there's no guarantee that it'll work well. Maybe you'll get lucky or confused for a little bit. Yeah. hmm The so you could do it that way. There are a few papers that approach the like constructing levels or hierarchies of policies that way. It does end up getting really tricky because like if you start at the top, then you have to generate a policy, right? That now can be controlled over some distribution of tasks. Every time a policy is generated, it's essentially a brand new MDP to the policy up top. So there's this big change in like the distributional. It may have these options in other policies, but it's kind of like uh, maybe I'll use this kind of weird example. It's sort of like if you were walking and then, I don't know, I ran by and I changed one of your shoes for a big giant boot, something like that. You might at least need some time to adjust your walking. So it just becomes it's a really hard challenge and generalization problem when you start from the top. Most of the time, most papers will start from the bottom, partly because we have a lot more engineering knowledge of like how to make low-level controllers, and then we just try to replace them with a learned one and then we can build on top of that. But we still face the same problem. It's like, okay, we want to introduce something new to that low-level controller. Now it's like you're changing the whole MDP for everything above it. You have to retrain everything in this whole stack. So you have to be like kind of careful in how this is going to be constructed because any change essentially looks like a whole new problem to most of the hierarchy. No, but like that is the heart of the problem though, of like dealing with these in terms of like the technical challenge is, well, I'll still talk about how to make some of these, but then we'll talk a little bit later about like, well, now how to think a little bit more about how to make them more useful and less disrupted if something changes about the hierarchy. Mhm. So here's maybe one of the first tricks that we could try in order to be able to get this to work, at least to make these a bit more generalizable. So this might be a better representation for the policy because it's more reuse. Um, but we're trying to figure out how to make a policy that could be a combination of other things. So let's consider this task. Here's our grid. The task is just to go to a particular location in the grid. Um, then, so basically, if we now wanted to enumerate all of the locations, and I'm pretty sure the grid is 10 by 10, you're going to need at least a one hot vector size of 100, because that's the possible like locations or combinations from these two different items. All right, can we do a bit better than this? This one's actual question for the class. Any thoughts on maybe how to adjust the way the contextual vectors are constructed to at least attempt, I won't say to cheat, but at least adjust distributions here? Yeah. hmm Why do you think that might work? hmm True. So then let's like maybe this option will do better. So there's a version of this. Yeah, we're like, if we split the context for the way this is being learned, so you've got one that basically just figures out like one X, one Y. So I haven't gotten as far as like training policies for this, but it is possible to express the goal that is desired here with these two separate one hot encoded vectors. Just pretend these are both of length 10 and not 5 on the slides right now. At least there's fewer dimensions here. So this makes the context smaller, but it can also provide another structure that can make this a bit more useful as well. So yeah, so now can you do even better than this option? You think so? Sure so. So, all right, how do you do better? So how would we split it up again this time? All right, don't store the zeros. Uh, yes, I think a version of that. It's kind of in this case, can we go back to, let's say, maybe I was a bit harsh on the like, forget a bit about the part where I said like you want to have a large vector just because it helps with deep learning. So just kind of think of this as like a numeric problem. So one option to be able to do better uh, is goal conditioned RL. Yeah, okay. And this is what we're going to talk about some more. Sorry for all that. So then here it's to actually give it an entire goal, because now the idea here is that there's this X and possible Y, is there still like fewer context dimensions, and I can specify a goal that's kind of decoupled this. So now you could just, for basically every continuous feature that may exist upon some particular goal space, you can kind of discretize those into the continuous pieces. And I'll get a little bit more into one of these examples in a second. So now you can just basically, if this was some random combination of tasks, then this becomes a version of goal condition RL. So like now it's not just a context. One of the parts of the point I'm trying to make here is don't just enumerate all possible goals and have a really long one hot vector. Now what is often used in goal conditioned RL is basically to have this goal, and the goal, maybe this will help. The goal really comes from the same distribution as the state space. Because you could just describe like, go to this point, quite literally. So no more long context vector. Now it could be like the numerical values that are used for that specific goal. Okay, does that make sense? We'll get into another reason in a second why this ends up being more helpful. Okay. Um, so this is basically taking this context conditioning one more step where now you don't have the vectors, can use the continuous states. Okay, A brief aside for a second, just depending on if you go reading goal conditioned papers for goal conditioned RL, some of them totally drop a lot of the notation that's used for reinforcement learning and finding goals, and instead write it like this, where this is the probability of some state in the future being the goal that was specified. And then like the sooner this happens, the better. Like the sooner the agent or policy ends up finding that goal, the better. So then you can construct this, given some state, that's the initial state, the kind of expectation you want to maybe be able to optimize over is making the goal state equal to that future state in some way. And then there's a discounted version of this. So this will help encourage like getting to that goal within, earlier times rather than later times. Okay. Does that make sense? Yeah. So this part doesn't quite solve that, but using this goal conditioning solves that. So here it's now we don't have to have the vector. Now this is one policy that takes the state input and we're calling this like a context representation that can basically describe anything that's in the state. Because before it was a combination of policies that we're talking about, and we would basically like select a policy as if it was an on or off switch. Now this is more like here's a goal that is like a continuous representation over all the possible policies that could be available to solve this task, in particular for that goal. So I think part of what you're getting at is a second challenge of figuring out how to good representations over this space. We'll get to that in 2 more slides, but right now this is just, okay, we've got one policy that we can express, and it can still get to all of the possible combinations of goals that were talked about before. So it's just a bit of a description at the moment. Okay, but otherwise, yeah, hold on for like 3 more minutes. Yeah, and then here, like I was saying, where this st plus 1 just happens to be a variable in the future, and then maximize basically the policy gradient for pi in order to be able to, make it such that the agent reaches that goal quickly. It's just another way to see this, but if you go and read at least 1 or 2 of the papers that I'll post for like the next lecture, they're going to use this notation. There's going to be very little RL in there, and this one will show up, but it's basically the same thing. It does make it a little bit easier to talk about reaching goals and the probability of reaching goals rather than just doing it in RL. Okay. So then back to a version of this for our first goal conditioned RL algorithm. I know everyone was waiting very patiently. The nice part is this doesn't really require a lot of change so far. Like in our typical reinforcement learning pipeline that we've been using, really the only thing that needs to happen is someone needs to come up with a distribution that generates potential goals. Uh, let's just say that's easy for now. It's actually really hard, and we'll talk about that in the entire second lecture. But for now, it's just like pick goals that the agent could satisfy, give the goal as part of the input to the policy, and then train it as if you were basically just doing normal reinforcement learning. So it's a pretty powerful paradigm. It's pretty easy to wrap around any kind of RL that's already being done. And then you can have a policy that doesn't just do one thing. It could cover all the like cutting different types of vegetables, as long as you can specify that in the goal. So this is where goal conditioned RL, not specific to any RL algorithm. You can do this with PPO. It's more typically done with off policy algorithms. But I think that's just a habit of the people that typically want to do goal conditioned RL are trying to already try to like save space, save sample efficiency, and have a policy that can be given a bunch of different goals. More so PPO is used for, here's a big giant problem, we can't even find a solution, and here's $1 million of compute, and maybe you can optimize that well enough. Okay. Any questions so far? All right, because we'll make many edits to this over the next, 50-ish minutes. Okay. Now I think we're going to get back to part of what you're asking about. Is there some generalization that can happen between goals? So if the idea was to go from right now, the policy is trained to go from, let's say this is 0 at the bottom, which makes this, that's G1 over here. Oh, sorry, G0, G1, and this is 4, 7, G1. Okay, if the agent is trained over its like that distribution on the last algorithm to be able to go to G0 and G1, will there be some generalization between goals in this case? So here, this one isn't so much of a question you have to worry about, but it'd be a nice option because now it's kind of a lot of work. Let's at least say if we need to sample a goal like across this entire grid and now train the policy to get to every single one of these goals, this is going to be likely not more sample efficient. This is going to be far less sample efficient because now it's kind of like there are 100 different policies. You need to solve 100 different MDPs in order to be able to get that policy that's now goal conditioned. Doesn't sound like the best option, does it? Like you're kind of getting this structure with a lot of cost. Well, the nice part is this often works. So if, where was that? 0, I think 4, G0, G1, something like that. Often if this is like G target, specifying that one for the actual policy, often that'll work really well. Like the agent or the policy will still end up going to that goal with some pretty good accuracy. And this is really one of the other benefits of doing goal conditioned RL. If the space of possible goals is sampled pretty good, then any other particular goal that some other system gives it later on, like in test time, it should still be able to satisfy that goal pretty well. Okay. Does that make sense? So, yeah. Yes. I mean, I'll say just a way to summarize that is it does depend on the smoothness of the space between goals and the smoothness of how the learned model responds to small changes in goals. So, because there could still be, all right, we're going to get into weird geometry time, but if there was a goal here, maybe if this was G0 and this was G1, okay, so if this is like a smooth space that's pretty continuous, or maybe I'll do this in just 1D. So if there was a goal here, G0, G1, and let's just say this is like the space, it's still pretty smooth. So you have to, maybe it has to go over this hill in order to get to the other goal. It's not quite linear, but it's still possible to at least understand when the policy was trained over here, there was an upward trend here and another upward trend over there. So when it tries to do some interpolation, and at least if it's guessing to be somewhat linear, it'll end up somewhere near the right spot. But if there is either in the space of goals or states some really odd geometry, like if this is another one for G0 and G1, and I don't know, maybe it's like this and it bounces around a whole lot and then goes like that. Okay, it looks like it should be smooth, right, between those 2 points. So here the state space is really weird. I think actually this particular chunk I drew here is impossible. So maybe don't worry about that one too much. But this also depends on the input space, like how smoothly is the policy now going to interpolate between these inputs. So the planning challenge outside of learning comes from at least like the bumpiness or really high curvature of the local space. But then there'll be the other like curvature of how well the policy is trained to interpret that smoothness. So this is maybe also a good point because typically people use goal conditioning on a very smooth continuous space, like it's navigation problems, like go from here to there. So there's no weird bumpiness in like the true environment. It's perfectly smooth and linear. and they just need to figure out how to capture that, and then it should be able to interpolate between goals. The parts that may also help, though, I know this is a discrete space here, but you could sample goals. So still some of this depends on like how good the sampling process was for training time goals. It might still like sample another goal over here, or maybe something along this space, and then it'll start to see, oh, actually, this is a mess, so it's not going to actually perform too well. So when it comes to the learning that we'll do, um, depends on the smoothness of our function approximator and the smoothness or density of the goals that we sampled. That's why it's tricky. And that basically goes back to like this paper for a bit. So even for high robot, the low level policy was trained over, sure, a bunch of language goals, but now those are translated into some language embedding space. So the ability to be able to generalize to new goals depends on the form of that representation in the embedding space in the language in the transformer, which is, I'll say at best, going to be kind of ugly. Maybe it starts to become more smooth that this gets trained over a lot of data, just as then it has to actually learn a good representation to express all those different types of sentences. So it's a bit of a balance. Okay, does that make sense? Other questions? Okay. Um, but this is still one of the features. Like a lot of the point of the feature here, first it was not having a policy for every single possible, like not having a set of parameters for every single possible policy, because you're basically wasting parameters. But an additional bonus that we kind of get out of this is like, well, now it might learn something about the regularity of the goal space, such that it can at least interpolate over goals. It does tend to struggle with extrapolating over goals. Okay. Yeah, but this is basically the for the agents that are making these algorithms, this is our goal. It would be like get a policy that perfectly meets all the goals in this grid while sampling the fewest number of spots in that grid. That is our like sample efficiency here. And this is really challenging to achieve. There's really not much mathematics that says how to do this. It's some way to get it to converge well. There's maybe a bit if your like policy is a linear model, something like that. But you know, those spaces aren't as fun. We like big, ugly, nonlinear models in this class. Okay. So, so we were getting into a lot of the like avenues of what sort of to do with this representation. This also depends. It's nice because it makes a policy now taskable. A lot of what we talked about in the class, if you kind of ignore the first few lectures where we did talk about kind of goal condition BC, but now this is getting into the ugly details about getting that to work right. It'd be making a task or a policy taskable. Be like, here is a description of what is desired to come out of that actual policy. Because before it was like, here's a reward function, go maximize that thing. But at the end, do we really want to have to like provide a reward function, have it trained from scratch for every variation in the thing we want to command the robot to do? No. I'll just at least say from the beginning, it is such a pain to write reward functions. You definitely don't want to do this because you'll need like two PhDs, one in patience and one in writing reward functions in order to start to get used to doing that. Instead, it's be really nice if we can have easy to use, understandable, human readable descriptions of tasks that can be given to these agents and then work from there. Okay. Um, so so then if our goal being the, you know, the agents that are making up the algorithms that are trying to search over this goal space the fastest. Now this is actually a function of that distribution that's generating goals. What type of distribution should be used to generate those goals? So there is at least one, we can start out with common one, uniform distribution. Just pick something in this grid and then use that goal, train to be able to solve that goal. Basically, if you're looking at a particular problem and you don't know where to start, this would be an okay place to start. This would be pretty similar to like for high robot, even if it's training language-based goals, there's going to be some like library list of all those text goals it could actually perform and just pick all those at random and train the policy to do them. It's okay. It can work if you've got a lot of compute and patience. It's certainly not going to be the more optimal version of being able to search over this goal space fast. If there is a little bit more information about the task at the moment, like what its goal distribution is going to be, you could try a Gaussian distribution instead. So maybe like put the mean somewhere over the more likely distribution of tasks that are going to be specified in the future, start to select around that distribution. That can work over time, but this is generally a pretty complex topic. And that's why we'll see if we get to it today. I've got like a whole lecture basically on figuring out how to do this well. And this is like a whole bunch of problems they're trying to figure out how to do this. Because this is also related to in the, high robot paper who is getting featured way too much in this class right now. No one paid me to do this. Maybe they should. But now like this high level policy is trying to figure out like what should be specified to that task, but it's not used during training. So there's no training that goes on where it kind of communicates across the goal space here. Nothing like that. Okay. All right. Does that make sense? Part of the challenge, like I was saying, kind of like in the regret space or sample efficiency, figure out how to do the sampling. Here's just two suggestions to like start with if you're starting to train a policy that is goal conditioned. Pick one of these two if you don't have really any other information to work with. Okay, how's everybody doing? How about we'll take a break there for now? Started a teeny bit late, but it's 1:54. We'll start again at 2:04. Mhm. Yeah, should be okay. Pretty well timed lecture. I did not pay the like physical intelligence people to put out that paper just before this talk. Happened to be lined up well. Yeah, works. Mm. Um, mhm. All right, everybody, get started again. I know we're all can't wait to learn more about conditioning on goals. Okay, so one of the things we were just talking about for a bit before the break was being able to handle the sample efficiency, because now part of the challenge is now every trajectory basically has a like it has a start, but it's always going to some goal that it's kind of aiming for, even if it's at some other state overall, and then maybe some other goal over here that goes over to here. Sorry, that's a state, close direction to get to some goal. And then basically now there's this huge space of things to cover. Because before, without goal conditioning, basically the problem is there's always some, I don't know, goal star to get to. And wherever the state is that the agent starts from, maybe I'll draw this inside of this area. It's basically always starting from the same location. It's basically like just figure out how to get to that thing. That's great. Um, but now it's basically start from anywhere, you have to go to anywhere inside of the entire state space. This is a much more tricky problem than just kind of figure out how to go one direction. So then, is there a way to be able to take better advantage of this experience that's been collected from the actual policy? So let's start with a bit of an example. Okay. One, okay, you were saying it's nice because we can actually have much better control over how the goals are selected. So even though, could start out here for some particular state, uh, what would be a good goal to try next? Maybe I'll pick some options here. This is A, this is B, and over here is C. If you were to start out training an agent from scratch, which one of these goals would be a good goal to give to the agent at the beginning of training? C, C, B, almost. How about A? Thinking about A, start from there. Okay. Because now that part of the algorithm is selecting this goal distribution, we have some control over this. We can now maybe pick this distribution. Maybe it starts around the initial state distribution. Something like that is a good option. So this can be used to kind of like more carefully do this selection process of covering the whole goal state space rather than starting way over at the very far end. Something like that that might take now a really long time to be able to learn that, and the agent can't even figure out how to get to locations like this yet at all. Could start out, for example, like near the initial state space. And this ends up being, there's certainly a lot of papers that do that. This is a form, no, it's not a form of continual learning. This is a form of basically learning and then expanding the difficulty over time. Uh, at the current time, the word is escaping me. It's not incremental learning or continual learning. Yeah, curriculum learning. Thank you. So this is basically curriculum learning. Uh, over time. And the reason why this can be really nice, okay, so one, you can kind of control the goal space, but curriculum learning is a general principle for just basically start out with tasks or goals that aren't so difficult, build on that curriculum over time. You know, I'm guessing some of you have been through some sort of education system where it's gotten more difficult over time and you build on things. So it's basically just using that concept, at least where the term comes from. So now you can control the space for this curriculum learning. And this is where if we've got some more information about the task, we can control the space even a little bit more. So maybe there's over like any possible MDP, could be tricky to be able to train a policy for all of that. And each goal is a new MDP. Sorry, maybe I'll go back to this part. But it could also be possible to like control this curriculum. Usually there is some goal to get to. I'll just keep drawing goals on here until I run out of space. But you can also like adjust the way this curriculum grows such that, it start out here and then just kind of get longer in some way over time until it eventually gets to something like E or C. You can kind of ignore D or something like that for now. And this is actually one of the possible ways to do structured exploration and reinforcement learning. One way is to try and come up with really complicated math around the exploration distribution. The other way is to figure out basically how to learn a good curriculum structure such that the agent kind of experiences all of the best steps of goals that gets it to its optimal goal at the end. Both of those are options for being able to do good exploration. Okay, so then just a bit about the details for programming these. So one, the goal is a new MDP. Typically the type of goal like reward function here is goal reaching. So here you can just take the current state and the goal, take the mean squared error, add a negative sign before that, make this as small as possible. That's an okay reward function to start with. It can get a little big. So if the agent starts out far away from the goal, this is kind of squared. So you might get really large negative values for rewards. I'll just say that's a part of a challenge with using this particular reward function. There are some variations on this. That's sort of getting to this point. On the next episode, basically, if the agent isn't able to get to G at all, you could try an adaptive system where on next time, okay, make G closer because it didn't get anywhere close to the actual goal. So you can control the curriculum even by making it a bit smaller if the curriculum maybe was overconfident in how far it could actually get. All right. Any questions about these, at least parts that end up in the code? Uh, Usually it's kind of just like a linear function and how it's increased. Usually, no, like just based on the number of iterations that have been trained so far. Uh, that just seems to work more consistently. So if you like took the same algorithm and tried it on some other environment, then it'll most of the time still work. The problem is now when you start to make it more dynamic, the speed at how fast these things should change depends a lot on like how the data was sampled. So you'd have to make a pretty good adaptive system. Um, that is a good point though. There are definitely a couple of papers that do that. Like the point of the whole paper is figuring out at like what speed should you actually grow and reshape this goal space. If you don't find any, or just like ping me on Discord, I can send you a couple of papers. There's even a couple of these that I've done. We just kind of like carefully grow this. And it depends really, like you can look at the Q function for the policy. Does it seem to be really high? Okay, then this is something the policy is already good at. Select something a little further away and like slowly grow this. And you can kind of pick stuff where the Q value starts to drop. And that's maybe where the agent hasn't learned how to reach that spot yet. It's a couple of different papers on that. Okay. Other questions? Okay. Okay, so this is kind of like doing some curriculum with the goal space. There is a possibility to do even a little bit better. So let's have a little thought experiment. We've at least discussed in the class a few times before. So you're trying to, or we've got an agent that's trying to get from A. The goal it was actually trying to get to is B here. However, because the policy isn't perfect yet, or there's some stochasticity in the environment, it actually ends up at C. So, in a non-optimal way. Okay, makes sense so far. What can we do with this information? So remember the original goal here was this. Like in the actual data set, B is where the agent actually wants to go. It's only going to get reward if it goes to B, but it stumbled or hasn't experienced this yet, so it only went to C. Do you think it's possible to be able to reuse, or at least somewhat use the data for it being able to get to go to C? It did go there. I don't know if you've had this happen before. Like maybe you're trying to go to like a restaurant that was part of your plans for the night, but it was closed, but you went somewhere else. Turns out to be your favorite restaurant for the rest of your life. Is that a bad thing? Could probably still learn from that, right? But then the only thing you need to do for the next time that you go to visit that new restaurant, you need to change your goal. And this is called, in hindsight, what happened. So in hindsight, maybe the goal was to get to this thing, but you didn't actually know that. In hindsight, you can go back, look at that trajectory, say that C was the actual goal to get to, because that trajectory knows how to get to C. It's got all the data for it. Doesn't know how to get to B, but it doesn't mean it's not the information to go from A to C. So you can basically relabel this process. So if A, B, and C was here, now go back, relabel that trajectory that was collected from the actual agent, and then here set all the goals to C instead. And now you've got a chunk of data with good rewards that actually gets a reward of 1 from going from A to C. So at least that data that was collected, still useful. Okay. Does that make sense? Yeah. Hmm. If it's possible to figure that out, that can be used. But here, one of the subtle details is it's only getting a reward of 1 at the very last state. So it's only when it finally gets to the goal. So it should at some point then, like giving discounted returns, if it found a shorter path that gets to that same location, starting from there, it'll get more reward for that one. So over time, not perfect. It doesn't get like a reward of 1 for every step, but at least here, this through RL and basically like discounted rewards can start to figure out to find the more optimal path. But it's hard to know which part of this is optimal. Um, You can still cheat a little bit more though and get that information. Uh, I don't think I'll talk about that here, so I'll just mention it now. Because this is basically, we've got access to some amount of information that we can use here. Because here we know that the agent got to C, like no matter what, because we can just take the state at the very end of the trajectory and it like perfectly got to that, no error. But there are other ways to reuse this too, because it could be instead like use our reward function that's negative s minus g squared, and then go in and relabel all of the data in that trajectory. But now this is going to be C here instead of B. So you can go in and like, if you wanted to do that, this would probably work better. It'll still, give it, it'll be able to tell it's non-optimal because it won't be finding the fastest path because some of these steps aren't going to be like the quickest along the error for the reward. But I'm mostly trying to get to that because we have access to the data and we technically know what the reward function is, we can use it to like compute over the data now new rewards for everything. And that would at least, it would be easier to apply here rather than trying to determine how optimal segments of the policy or the trajectory are. But I did purposefully draw the squiggly line because like most of the time these trajectories are non-optimal. So they're a bit helpful, like they're not zero signal, but they're not perfect signal for optimality. Yeah. Yes. I think you could definitely do that. So you would go back and add, I'll call this like C prime, like some other point on here. Could be a goal, just take that chunk of the trajectory and train with that. Um, totally good option. I don't know too many papers that have done that specifically. Okay. At least that are related to like the hindsight experience replay paper. But like a version of what you're asking about is also a pretty important task. Because a lot of times, like maybe there is a trajectory that goes from A to C, and if that's a long trajectory, how to specify sub-goals along the path. So what you're also asking could also be a good solution for maybe like finding good sub-goals on there and figuring out how to split this. In fact, I'll just keep doing this. It's half of what this paper does. The policy on the top, basically pick good points along a path that we already have the answer to in order to follow it. And then the bottom policy is now figuring out how to do those segments. So definitely a very common, still somewhat tricky problem, figuring out good subgoals. Okay. Uh, all right. Good. Other questions? All right. So this is gone. Okay. This is hindsight experience replay, at least like specifically for this version. There are many modified versions of being able to do this to take advantage of data. The one caveat I want to make sure to share is that just be a little bit careful when you're using this method. The one thing that tends to come up is don't over label the data. So like actually if the algorithm relabels everything 100% of the time, it gets into this kind of like bias situation where now the policy thinks like no matter what trajectory it rolls out, it always gets to the goal. Every single thing in the data set says that it's perfect. So it's going to get a really high Q value and actually be terrible at getting to like goals in general. So a rule of thumb here is like don't relabel more than about 30% of the data set with hindsight experience relabeling. It still will normally give you about like 50% better sample efficiency while using it. Yeah. Okay, sorry. So you've managed to get to C a few times. Okay, and then some point later you want to go to B. It still ends up going to C. Mm. Um, Yeah, I would include that in the 30%, like any amount of initial relabeling. I think this will also be a use case that happens quite a bit because the policy will then get good at getting to C, and then you'll try to tell it to go to B, and it's going to go straight to C because it doesn't know any better. So that's also part of the challenge is if too much stuff is relabeled, it really overfits its current distribution. It's basically going to randomly initialize to following some pattern and just never learn anything besides that because it's always going to be told, oh, look, you always manage to get to C every time. So you really need to not relabel it too much so that it learns it's not good at stuff and tries other things. Okay. All right, so then this is like the small adjustment as we keep building on our goal conditioned algorithm. So this is still the same. To be honest, that part is still the same. There's a slightly different replay buffer now that'll be stored. And then there's just a bit of a change here, which is, uniform distribution. So this is basically then the less than 30% of the time. Go back in, put basically S of t is the state at the very end of the trajectory. Just go back in, replace what was the goal. So if you look at this, like the goal is the second item, go in there, replace that goal with the final state in the trajectory, and then label one, a reward of one for the very last time step. So basically, if you've got a goal condition policy already, you just add these 3 lines of code and we'll do hindsight experience relabeling for you. Ends up speeding up your algorithm pretty quick. Okay, makes sense? Almost too simple. The basic version is pretty nice and simple as long as you follow like this 30% rule. Okay, so that one is pretty simple. All right, so I've got an annoying question for you this time. So it's not always easy to specify every task as a goal. All right, for example, what if I gave you the goal, run to the right? How do you specify that as a goal? I'm sure you spend a lot of late nights up thinking about this particular problem, like I have. But now it's just literally like go to the right. Do not stop going to the right. Can you specify this as a state? But you'll have an end position. But I still want the policy to go even further to the right than any end position. Yeah, you could maybe do that with like enough band-aids. It'll just be like your current goal state is always like 10 to the right until you go crazy, but that's not always the easiest one. I can also give another one, which is actually like run to the right. So your goal is like highest velocity to the right. The reward function is literally just like velocity in X direction. At least that's what it is in like the code. But how do we specify a goal for this? Yeah, no, I'm being a little bit annoying at the moment. You can't really, like, not in the framework that we've talked about so far in the class. Okay, so then what do we do in these cases? Uh, we need something a little bit different. And this is from what we've talked about so far. So this is instead of conditioning a policy on the context, we're going to kind of rewind a little bit back to before when we had a couple of different policies and talk about how we can maybe explain some of these under that uh, basically representation. So if it's not possible to represent this task using goals, what should we do? So we've at least got, you know, you could literally code down the reward function for now. So this is like run to the right. If you're at least a little bit familiar with the homework code by now, agent.velocity.x is basically could be the reward function or run down. Now we've got a reward function for running to the right and running down, and they're not based on states. We don't have a representation, but at least we're talking about the same concept right now. Okay, so it is possible though, going back to the beginning. So now we can train a policy to optimize each of these. So we've got policy run to the right and policy run down. Makes sense? So at least we've kind of covered 2 of the cardinal directions on this particular map. So what if it's What if it's desired to have the agent run to the right and to run down? How could we make that happen? Do you think we can maybe try and add these policies together? Hope. Well, a little bit more than hope here on the next part. Okay. So let's not think about the policy space. That's the part where we're making a bit of a jump here. Is these are the policies for how these things are actually being like learned. What does this look like when we start to talk about Q functions? So now we've got a Q function that says like run to the right at this particular, at the most speed and run down at the particular most speed. And these Q functions basically say like, if you select this action here, this is how good you'll end up getting these rewards. How can we possibly take advantage of that mechanism? So if you remember, like, especially when we're talking about Q learning, we do like a max over all actions in order to be able to achieve, like, this is the action that maximizes that reward that it was trained over. So now if there's a bunch of policies, I'm pretty sure that should be a Q function. Basically, now instead, optimize for the best action depending on some mix of MDPs, or in this particular case, Q functions. So now that there's some like collection of basically functions that determines how well it will do with that particular reward, or really just like score in general, take a sum over these Q functions. So now it's argmax, find the best action that results in the highest Q value for both running to the right and running down. And now it's possible to, like, when these are mixed together as the agent selects actions, it can eventually like find the action that is at least somewhat a trade-off between running to the right and running down. And here, a lot of the concept is like baking this into the Q functions, relying on the Q function to have a good representation and being able to generalize to this sort of mix, but this should work. Yes. Yeah. So like in this case, this will select the one that runs to the right with 10, because it's just going to do the sum. It's not any smarter than that right now. That'll rely, so part of the challenge with using this is relying on being able to learn a good policy and Q functions and then hope that they mix together. But that's one like good example of part of the challenges with this. And that's sort of like the more ideal example, because you can, if you don't know like the specific structure of the policies that will be trained, if it's all of these arrows, if you're trying to mix this Q function and that Q function, they kind of cancel each other out. Whichever one had like a slightly higher Q value is probably going to take over the entire optimization. So a bit of the challenge with using this method is some more knowledge needs to be known about the reward functions beforehand, or at least the Q values, to start to get a bit of an intuition for what's going to come out of this like online maximization across Q functions. Okay, but then so to attempt to adjust for this without kind of changing the policy structure, what often is done instead is like just add a little weight here. So like now, at least online, there's another weight. So if it seems to like always be running to the right, well, I'll reduce the weight on that a little bit more, and that might help get a down to the right policy instead of a just to the right policy. This is also really helpful if there's no like normalized scale between Q functions either. This particular example is very much, it's not overfitting, but it's like the ant running in directions. The nice part about this is it's supposed to be like describe any reward function, any combination of them. So it could capture any type of thing you're trying to train the policy for. It just might require a little bit more background knowledge to understand how to use this, because you'll often need some good knowledge about what the Q functions were originally modeling to use it properly. Okay, does that make sense? It's a bit tricky, but this is just sort of a weirdish conceptualization of Well, if you train an agent on more than one Q function, still the same state space and action space, when you go to do the argmax, you can actually mess around with this argmax and try to get some other behaviors out of it just by doing some combination. Um, this is related to successor features, to which there's a really quite a large number of papers that can also be added to this, but it's like learning how to train this well. A lot of these papers are trying to figure out how to like carve a good trade-off between like learning a representation and getting Q functions that make sense and still getting good behavior. It's still a bit challenging to get like everything that we want out of this particular method, but it also generalizes pretty well. Okay. Yeah, any other questions? Pretty good on this one. Okay, this has been used for a few papers recently. I guess we went over it really quickly, but if you also remember the RL0 paper, it's kind of using something like this, where it like trained the policy that'll work over a bunch of different types of rewards, and then it would specify like that vector from the forward backward algorithm. That's sort of another representation of this, of figuring out just how to like infer a policy really quick over all the distributions of policies. So a lot of the stuff we've talked about before is now connected here, but we're getting more into the details of what those algorithms are doing. Okay. All right. So I might skip this for now. All right. I don't know. How many people have written a wrapper around an OpenAI gym environment? Everybody? No? Okay. The basically it's sort of like, well, how do you actually implement goal conditioned RL? You take like the original environment that was an OpenAI gym environment, put it inside of its own Python wrapper. Maybe I'll just show this real quick. And this is usually how like the goal conditioning is added. Where just basically you've got the like original, this is sort of for a goal condition policy. There's always, I thought there was some, yeah, there's some in it somewhere. And then it's going to sample some tasks. So like here's the process of like just picking some random goal at the beginning of an episode. And then you just sort of add a few more details around the original simulation. So if this was the original simulation, can get the X position, compute the cost, which is just at like MP squared error sum, which somewhere in here is multiplied by -1, probably in here, control cost, and then be able to use it as a reward. So it's just really use the prior simulation to do the actual like simulation step, grab the reward and goal position, compute the reward error, and then just like, have that be the actual reward that comes out of the new model, or sorry, like the new wrapper around the simulator. So if you go into more and more of the ugly details of like the wrappers that are put around simulators for RL, they're often very oniony. And by oniony, I mean there's like many wrappers on top of each other for all sorts of things. So this is just one more wrapper you could add around the environment, and it implements the like entire goal conditioned RL algorithm. It's just this. The actual RL algorithm doesn't need to change, just this wrapper. So your goal conditioned RL is about 30 lines of code, more or less, as long as you're not doing anything too complicated. Because I suppose if you're using a language model, then now this line here is like feed in some text description for the actual goal, get out some embedding, feed that embedding into the policy up here, and do all the same process. So just be editing a couple of these lines a bit differently. At least this is the goal wrapper for when we're not learning something about how to change the goals. Okay. Any questions so far? All right. Yeah. I will say, like, for most of all these problems, it usually is just like sampling a single goal at the beginning of an episode. It just seems that like that wasn't too problematic for a large number of tasks, but maybe for some other really stochastic environments, it might be better to like use a goal for more than one episode, like keep it around so it's not so noisy. Because remember this, the probability distribution over paths kind of depends on the goal. So if the goal is changing very frequently, that's even more variance over the trajectories that are being generated. So that'll just make life a little trickier. Okay. We've got a few minutes left, so let me at least introduce this for a little, for a short bit. So this was just regular goal conditioned RL, and then at least just to get into this. So this is now visual goal conditioned RL. So now the state is no longer a state, it's an observation. And the hope is to be able to do a lot of the same structure all over again. Go through a couple of details, but now think of goals this way. The idea is here's a robot, really happy, is really excited about being told what to do. And the idea is here's the image of basically what is desired to be like the configuration of the world. And the hope is that the robot will replicate this particular configuration and to train an agent to do this. So now this doesn't have to be state conditioned, and it would just be an image. At the very least, this ends up being really helpful. Let's say, for example, I don't know, I'm trying to put a symbol in here that says like, well, the rotation of the plate doesn't really matter. If the plate is well made, the whole thing looks symmetric. So then like in state space, normally you're like the agent would be trained to force to find like a particular rotation for the plate. It's not really needed. It's something we can normally ignore. So if we can train these like this basically goal condition model to also work over representations that are invariant to stuff that don't really matter for the task, it makes the task easier to solve, and we get a fantastic representation that's probably a better way to express the state. Challenge is being able to learn these two things. We still have the probability of pass that we've talked about already. Still goals. Nothing's really changed there. Still trying to maximize reward. But the one thing that now we start to run into is, well, now this is going to compress some image model into some representation space. We may not have rewards anymore. So this makes this harder to train. This is may not have rewards. The part where actually this is still nice and working with the text model is a pain in is like if we completely go to a text model where we just feed in text, we really don't have access to a reward function. There's really nothing that says like if it satisfied that goal. There's definitely a couple of papers lately that will then like use another VLM and ask that VLM, did it satisfy this goal? But that's not going to be like 100% correct. And we kind of know like reinforcement learning doesn't like its reward function to be stochastic or not correct. So it may help, but it's a bit risky. But at least here already we're starting to lose from this. So basically, as we start to make this goal representation more flexible, it usually comes at the cost of it being harder to automatically compute rewards for the goals that were specified for the agent. So let's just get into this a bit more about this representation here. So there could be our awesome Baxter arm here on the left. There's a lot of details in this image, but for the most part, a lot of them don't matter. So the real question I might ask is, okay, you can hopefully notice the same change. I hope no one is colorblind in the class. Uh, Not that that's a bad thing, but just because of my poor planning. But basically, is this thing still a puck? So just because the color of this puck changed, like the task doesn't really change. It's still this object. The task is still to probably move this object from one location to the other and figure out how to just, remove and not care about a lot of the background noise, not really care about certain changes in pixels, where most of this seems the same, even for coloring. And basically, the challenge is now this image is a really high dimensional. And actually, the task and parts of the state that are of importance for the task are really small. It's actually only about like two-dimensional, just the like location of the puck, even though there's probably 30,000 pixels. In this, the state space that's task relevant is two-dimensional. And we need to be able to learn that. So this is all about this problem again, learning a good space that goes from basically observations to states. It's always about learning a good distance space such that things are meaningful with respect to the problem we're interested in. So here in this space, it's figuring out, like learning some particular blob here that is now a good represent place for representations or encodings that makes sense in the task space, where at least this distance is like more or less correct. Yeah, that makes sense so far? Yeah, everyone's still with me for the last couple minutes of the class? Or is it just everyone's real excited for the weekend? So then this is like learning this more meaningful distance space, noise is ignored, all this good stuff. Because really part of the challenge in just doing robot learning is learning to ignore a bunch of stuff the policy should be invariant to. A lot of this is just starting in that space as well. And maybe I'll just go with this one last example. This is often called, like in the literature, comparing two things. One of them is basically you can do distance in geometry space or distance in appearance space. So if you're looking at one of these two humanoids here that are like digitally rendered, a lot of it has to do with like the importance in state space.